7th installment of PNNL's live virtual communities tour series. This 8-week series is intended to introduce you to the spaces and instruments behind the science and impact at Pacific Northwest National Laboratory and the world-class research that is taking place right here in the communities in which we live and work. PNNL is one of 17 Department of Energy national laboratories. And at PNNL, we are advancing scientific frontiers and driving innovations that enable sustainable energy and enhance national security. Chemistry, earth sciences, data science, and biology are foundational at PNNL and underpin not only our scientific discovery, but our applied work as well. Our work to advance sustainable energy includes focusing on decarbonization and energy storage. And our national security expertise enables impact related to nuclear materials and threat analysis. We have about 5,300 staff and a diverse research portfolio that drives about $1.2 billion in business each year. Last year, we had nearly 1,300 peer-reviewed publications and 340 invention disclosures. So that's just a little bit about PNNL, and now I'd like to move right into the tours. At this time, you'll hear from Ryan Eddy, who will give you a brief introduction to tonight's tours. Ryan has been with PNNL since 2009 and is currently the Director of the Homeland Security Programs here at PNNL. In this role, he oversees the work PNNL does for the Department of Homeland Security that encompasses nearly 50 diverse projects. I'll turn it over to you, Ryan.
Great. Thank you so much, Megan, for that introduction. I also want to extend a warm welcome to everyone joining the visit this evening. As a multi-purpose Department of Energy National Laboratory, we have the privilege of working on diverse subject matters that directly impact our local community, our nation, and the globe. One of those areas includes our work in national security, as Megan mentioned. Later this week, our nation will mark the 20th anniversary of the events of 9/11 that had such a profound impact on all of us. In the early days after 9/11, PNNL was called upon by government leaders to help put our scientific expertise to use in protecting the homeland. That early work has now matured into long-standing support for the Department of Homeland Security. In my role at PNNL, I help to oversee the almost $80 million worth of work we have the honor of performing for DHS. That work draws upon PNNL's world-class expertise in explosives detection, cybersecurity, data analytics, chemical and biological forensics, critical infrastructure protection, and radiological and nuclear detection. This evening, you will have the ability to see the one-of-a-kind facilities at PNNL that are helping to aid the diverse missions of DHS. First up is my colleague Dave Sheen, who will be showcasing our explosive detection work that is leading the way in developing protective measures at airports across the country and globally. We will then end the tour with my colleague Kevin Doro, who will take you on a tour of a facility you will not find anywhere else in the country that is ensuring that our ports of entry are safe from radiological and nuclear threats. Thank you again for being here this evening. And with that, I will hand it back to you, Megan.
Great, thank you, Ryan. And like you said, I know you are introducing Dave Sheen. I would like to formally introduce him and turn things over to Dave. He is a laboratory fellow and electrical engineer in our National Security Directorate. So Dave, why don't you go ahead and take it away?
Great, thank you, Megan. Yes, I'm Dave Sheen, and I'm the team leader for the electromagnetic sensing team and also the program manager for millimeter wave technology at PNNL. And I led the team for many years and currently lead the team that develops and developed the original millimeter wave scanning technology. Most of you are familiar with that technology. It's in the airports today, all over the nation and the world. And we're currently working in that area, developing new technology. And I'm going to show you both the history and also some of the current developments in that area. We're going to kick this off with a short video that introduces some of that history and technology, and then we'll follow that with a live tour of our laboratory. So back to you, Megan, to kick off that video.
Welcome to the Engineering Development Laboratory, or EDL. This building is home to the microwave and millimeter wave imaging capability at PNNL. That's embodied by the electromagnetic sensing team and also the millimeter wave technology development program. Our research is driven to a large degree by some very high-profile security events. The mid-1980s, there was the Moscow bugging incident. 1988, there was the downing of Pan Am 103. 2001, there was obviously 9/11. There was also the shoe bomber. What we specialize in here is microwave and millimeter wave imaging for a variety of applications. We usually use microwave and millimeter wave imaging to do things you can't do optically, typically looking for concealed threats. All of these incidents had a profound impact and drove interest in the research, and in many cases led to significant funded programs here at PNNL and within the millimeter wave program.
Great. We'll continue the tour. I'd like to start a little bit, as mentioned briefly in the video, what the team here does is electromagnetic sensing or microwave and millimeter wave imaging. And we do that for a variety of reasons, but most commonly it's to look through things that you can't see through optically. So that includes a wide variety of things. And we have a number of focus areas that we've worked in over the years and currently shown on this poster. It includes things like ground penetrating radar, looking for buried mines or other objects in the ground, looking for objects concealed in walls or behind walls, looking for hazards, typically explosive devices, perhaps hidden in the bushes on the side of the road. And of course, the body scanning technology that we've been pursuing for many years and are still working in this area aggressively today. Also things like looking for suicide bombers at greater distances, ranges of 10 meters or even further. So those are a few examples of what we mean by, looking through things that we can't see through optically. In all of these cases, we can't see the threat with a normal video camera or infrared camera. So our technology attempts to, and succeeds at forming images that allow us to see through these types of barriers. So with that, I'd like to continue on and do a bit of a laboratory tour and show you some of the equipment and the technology that we use to conduct our work. But before I do that, I'll dive just a little deeper into the history. The little video segment gave some samplings of the history, so I'll go over this fairly quickly, but the team actually dates all the way back to the late 1960s, doing work in acoustic imaging. This was developing acoustic holography techniques. Founder of the team, Dale Collins, developed many novel techniques. He adapted those techniques to microwave imaging. And we did work starting in the late 1980s, looking for objects in walls, also looking for concealed threats. So our work actually predates 9/11 by many years. We were really early pioneers in this area, developing ways to see weapons hidden underneath clothing, whether they be plastic or ceramic or any other form of material. We can potentially detect them. And we developed early prototypes in the 90s, developed a cylindrical technique in the 90s that we evolved into a first prototype system around about 1997. And we licensed that technology then to a startup company called SafeView. And they got started about 2003. They developed a prototype based on our technology that they licensed from us. And then they sold their company and their technology to L3 Communications, which is now Leidos. So the systems you see in the airport today, many of them are branded Leidos, but all of these systems, I believe there's over 2,000 now in the airports, use the technology developed at PNNL. And we continue to develop advanced prototypes in the last few years. This includes a much higher resolution version of the cylindrical scanning, a shoe scanner and a subsequent shoe scanner, and additional prototypes. And I'm going to show you a little bit more about that as we continue on in the tour. But first, let's talk about some of the just basic equipment that we use here in the lab. That includes things like you see behind me. This is a vector network analyzer. So this is a very expensive instrument. It can be used as a radar transceiver. It can also characterize microwave and millimeter wave devices. I forgot to mention, but microwaves and millimeter waves are basically just high frequency radio waves. So so we use high speed and relatively specialized electronics, but nevertheless, we can use electronics to produce these signals and characterize devices using instruments like this vector network analyzer. We also use this analyzer coupled to an XY scanner, and we can use this to develop feasibility experiments that prove out the concepts that we use. And we actually used this very scanner back in the 90s, doing some of the early work at developing the imaging techniques that are in the airports today. So we show this scanning. So this is a low-cost way for us to experimentally collect data that would be similar to what would be collected from a high-speed practical system in the airports. Behind us, you notice there's a very distinctive, massive blue wall. That wall is filled with radar, or covered with radar absorbing material. We installed that over 20 years ago. We were doing some vehicle imaging, so imaging of large scale military vehicles to learn about their radar properties. And we still keep it today. It has kind of sentimental attachment to us. It's just always been a part of our building. And so we're fond of it. We keep it here today. Over here, you can see we have another vector network analyzer. So these are very popular instruments with our team. They're used extensively. They also have some additional instrumentation that's tied to this large anechoic chamber. This chamber is filled also with radar absorbing material, and it can be used to do very sensitive measurements. The system blocks out any electromagnetic signals from the inside, so you can do very sensitive measurements. It also blocks reflections, and so you can use it to do antenna measurements where you don't want to have significant reflections from the environment. So that's part of our laboratory here. In the conduct of our work, we do a lot of antenna design, and in some cases we just purchase fabricated antennas, such as this horn antenna that is used in the microwave range. We also procure conventional devices. This is a switch that connects one input to multiple outputs. But we do a lot of our own internal antenna design for very custom applications that end up in our imaging devices. Shown here are some spiral antennas that are useful for a variety of applications. They produce circular polarization. This is an array of several spiral antennas. You can't really see the spiral. It's actually on the back side of this device. This is a horn antenna, and this is a test fixture that we made. You can see that's a same horn antenna design used on this array. This has integrated electronics that allow us to switch between these outputs and can form the basis of an imaging system. That's an example of technology that we've developed here. And a similar technology has been incorporated into multiple prototype devices that we have made and delivered recently. So as Ryan mentioned, we do an extremely large and significant amount of work for the Department of Homeland Security, in particular their Science and Technology Directorate. One program in particular at DHS that we are sponsored by is the Screening at Speed program. This program really targets increasing or improving the passenger experience. So doing that by reducing false alarms and improving detection, but also increasing the convenience to the passenger. It's a very significant concern for both DHS and TSA. They recognize that we're all inconvenienced at the airports, and they are working hard and employing us to work hard to make the process more enjoyable or more reasonable. So we have 3 primary project efforts right now with DHS. That includes HDAIT, which is developing higher definition, next generation cylindrical systems that could potentially have additional sensors like a shoe scanner or metal detectors or even vapor detection. We're not funded to do that level of integration yet, but that's certainly on the timeline or on the roadmap for development. We're developing a shoe scanner project. We've delivered this to our sponsors in the last year or so. This scans up through the shoes, and I'll show a little more of a demonstration of the shoe scanner technology, but it looks upward through the shoes for any concealed threats, similar to what the shoe bomber attempted to detonate on that flight. And then our final primary effort with DHS is developing real-time or video rate imaging, and I'll show you a little bit of a simulation of that in a moment. The HDIT project will be familiar to most of you because it operates very similarly to current airport scanners. We just have much higher definition, higher quality arrays in the system. And the goal is to produce imagery that looks like this. And this is actually a physical simulation. So this is not actual data, but it's realistically simulated data of and it shows what's possible with this kind of cylindrical scanning. So we get very high definition, 3-dimensional resolution from the target, which in this case would include a person. This shows a quick demonstration of the shoe scanner. It takes about 2 seconds to scan. If you look really closely on the video, you can see the system move underneath. This may not be apparent for you on this video, but there's linear arrays that move underneath these plastic windows that the person is standing on. And data is collected, and we form that into a high-resolution 3-dimensional image. And then we can look at different depths into the shoe, and that shows different features, including the toes and the feet. And we've had in the inset image, we show one that we've embedded some targets into. So as we go through this, you can actually see the shoelaces here. And then as we move from the sole deeper into the shoe, closer to the foot, we can see these embedded targets that we've put in there just for test purposes. So that's a quick demonstration of the shoe scanner. And then our third project that we're working on is something we're extremely excited about, and that's the real-time imaging capability. I mentioned the founder of the group, Dale Collins. This is something he wanted to do 30 years ago, literally, and we lacked the technology to do it, but we're beginning to develop that technology today. This shows a simulation. I put up the total recall reference just because people always ask us about that. There's a famous scene where he walks through a very large scale concealed weapon detection system that looks like a large X-ray system. So we're envisioning a day when we can do that with millimeter wave technology. This shows a millimeter wave simulation of a man walking past a large scale real-time microwave imaging system. So I'd like to summarize or conclude the tour by just mentioning some of our accomplishments recently in aviation security. So this has been a very large area for us. We've developed several prototypes that we've delivered to DHS in the last year or two. We also recently won an R&D 100 award for the shoe scanner just last year. And we've licensed the HDIT and the shoe scanner technology recently to a small startup company. So we hope to get that technology into the airports in the near future. And then, of course, as mentioned, we're currently developing new technology beyond what you've seen here. And most of you are familiar with this pose. This is referred to as the PNNL salute. This photograph was just from recognition of the body scanner being a highly successful commercialization technology. So with that, that's a quick tour of the laboratory here. This is the Engineering Development Laboratory. And again, it's home of the millimeter wave technology at PNNL. And with that, I'd like to send it back to Megan.
Great. Thank you, Dave. And all of you who are attending tonight, please feel free to pose your questions in the chat window and we will get through as many as we can in the next 10 minutes. So Dave, the first question is, what led you to this scientific field?
That's a good question. It actually was Dale Collins. I had an internship here back in 1986. So I was here right at the beginning of this technology. He was in the basement of an adjacent building and did not have this glorious building yet. He also, I had just finished a bachelor's degree and he encouraged me to get a PhD. He had one and my brother was in the process of getting his, so I was inspired by that and did apply to graduate school and pursued a PhD in electromagnetics, electrical engineering, a focus in electromagnetics. And then I love Richland. I love Washington State and the Northwest, and so I wanted to come back here. And I didn't necessarily know that I was going to come back and work in this specific area, but I couldn't resist it. I love this area and I'm very much interested in the technology that Dale was pursuing. And so I started my career after graduate school with Dale in 1991.
Great, thank you. Are there health risks associated with the millimeter wave body and shoe scanners?
No, the short answer is no. The longer answer is there are IEEE standards that govern the amount of power that you can use and expose people to. But essentially, millimeter waves are just high frequency radio waves, very similar to what's used in cell phones and other forms of wireless communications. And the power levels that we typically transmit are just a few milliwatts, as opposed to a cell phone, which is typically hundreds of milliwatts. And so we're orders of magnitude, which means hundreds or thousands of times lower than the established safety standards. This is a form of what's called non-ionizing radiation. And really what that means is just that the only known effects are just thermal. If you inflict enough power on someone that it actually warms them up, then it can cause harm. But we're millions of times lower than those levels. So essentially no health risks.
Okay, and when can we expect to see shoe scanners in the airports?
Well, that's a little bit up to our commercialization partners, but I would hope within 2 to 3 years that we would see it in the airport. But again, that's not really up to us or our commercialization partners. It's also up to the government. Most security equipment essentially needs to be mandated because it is a cost to the airlines and to the airports. And so it really needs, it's up to policymakers, whether a particular technology is implemented or not. But certainly we feel it's going to be ready in 1 to 3 years if that comes together.
Okay, and what about implants or pacemakers? Are those detected, or is there a risk to people who have those?
Again, at the low power levels, I would say there's no risk for implants or pacemakers. That's not an area of expertise of mine, so I claim no extreme authority. But microwaves and millimeter waves do not penetrate the body at these frequencies. They really only hit the very most outer layer of skin and then are reflected. So there's very little penetration into the body at these frequencies. So there should be no effect. There should be no ability to reach a pacemaker or other device. But if it's mounted external to the body, it's possible there could be some effects. So that again, that'll be, the policymakers need to make the final decisions on that with some detailed analysis. But definitely if it's implanted well within the body, there should be little effect.
Okay, and do you think the development of real-time scanning could reduce, if not eliminate, false positive indications or alerts specifically triggered by bone structure, knee, hip replacements, et cetera?
That's a hard call. I think the cylindrical scanning is actually higher resolution typically. So I think it has a potentially better job of discerning the nature of detections. The real-time imaging does, however, have a strong advantage of you get to see multiple views of the object or the person, and that can allow some additional discernment that's not possible with a single scan as you would get with a cylindrical image. But I think there's, PNNL, as Ryan could inform you, is very has extreme volume of efforts or quality of efforts in artificial intelligence and machine learning. And I think that really is an area where the our expertise and other experts across the country can really be applied to reduce the false alarms, because I think it's really more a question of the algorithms used for detection. In some cases, they trigger off lines or edges, things of that sort, which may not be indicative of a threat. It could be indicative of something simple like a scar or an implant or something like that. So I think that's mostly a question of training the detection algorithms to be more aware of medical issues like that. But it is a strong concern because there's some lack of avoidability, because if a concealed threat such as an explosive could have any shape or size, and all we're really detecting is the shape and size. We're not detecting the innate chemical composition. So there's not much ability for an algorithm to differentiate between a benign concealed device that could be a medical device, for instance, versus a threatening object. So unfortunately, that may be part of the challenge. But again, a lot of that is in kind of the policymakers' realm on how aggressive they want the detections to be, because making the detections more robust always means there's more false alarms.
And Ryan, did you want to add in anything there?
Yeah, no, just to add on to the point that Dave made, we in fact are working in groundbreaking capabilities associated with artificial intelligence and machine learning that is really allowing us to look at these images that are manually reviewed in many cases by screeners at the airport or border protection officials. And we're beginning to see some great capabilities being developed to augment that process so that human in the loop isn't necessarily a part of that process. And it really helps to speed up that process and could potentially minimize those false alarms that are encountered, whether it be in an airport setting or at a border protection space. And you'll be hearing shortly on some of the work that we are doing in border security.
Great, thank you. And how will my privacy be protected when getting scanned by a body scanner or shoe scanner?
That's a great question, Megan. The principal way is through the artificial intelligence machine learning algorithms. In general, these images, like some of which I've shown you here, would never be shown to an operator anymore. When this technology was initially deployed, human operators were used to examine the images, but very rapidly they were replaced by automated detection algorithms that use machine learning techniques to detect threats. And as most of you know, in the airports, the threats are just presented on a generic avatar, and no detailed information is shown. And in fact, the images are by policy not saved from, only training images from volunteers who authorized or gave permission are the only ones that are ever saved. So privacy is protected by the policymakers and by the system designers by not saving the data and using automated detection in every case. Our particular specialty in this building is developing the imaging techniques. So we like to show the images, but the images of actual traveling public will not be shown or saved to anyone.
Okay, and I think we have time for one last question, Dave. Do you have gamma ray spectrometry in your laboratory?
Not in EDL. I know that PNNL does have a substantial amount of X-ray experience. Aaron Miller here at the laboratory is doing some groundbreaking research on phase contrast X-ray imaging for baggage detection. I'm less familiar with whether we have any gamma ray detection. Ryan may be able to speak to that more knowledgeably than I.
Yes, to answer that specific question on the gamma ray, we currently do not have any systems deployed here at PNNL, whether that be at our Richland campus or any other campus. We have in the past, and in fact, some of that capability had been deployed at the facility that you'll be seeing next. So that's a nice segue, Megan, for our next speaker. And thank you, Dave, for those excellent remarks.
It
Yeah, you're
was a
welcome.
nice segue. Yes, and thank you, Dave. Thank you, Ryan. As Ryan mentioned, now I'd like to turn it over to Kevin Doro, who will take you on the second part of our tour. Kevin is a project manager in the Applied Radiation Detection Group in our National Security Directorate. Kevin?
Thanks for that introduction, Megan. So just real quickly, you know, if any of you have ever crossed into the country, come across the border from either Canada or Mexico, you might have noticed some of these strange looking large rectangular yellow pillars and kind of wondered, I wonder what those things are for. Well, these are radiation sensors that are part of the Radiation Portal Monitor project that's put on by DHS. So back in the wake of the events of 9/11, there was some serious concern that terrorists who were emboldened by 9/11 would consider, you know, mounting an attack on U.S. soil using nuclear or radiological device, either nuclear bomb or dirty bomb. And the consequences associated with that kind of attack are so high that there were DHS components that were charged immediately with trying to figure out a solution to mitigate that risk and address the potential threat associated with that kind of attack. And so in 2002, the Radiation Portal Monitoring Project was started, and PNNL played a key role helping to try and achieve the goal of that project, which was basically to scan 100% of the conveyances coming into the country for illicit radiological and nuclear materials while minimizing the impact on legitimate commerce coming in. And so fast forward almost 2 decades later, and right now we have approximately 1,300 active radiation portal monitor systems that are deployed at over 300 ports of entry across the country. And that includes all the major land border crossings, seaports, international mail and cargo facilities, and pre-clearance airports. And together with DHS's Countering Weapons of Mass Destruction Office and Customs and Border Protection, PNNL continues to play a key role in the RPM mission, reconfiguring systems to evolve with port operations as they change, integrating new technologies, and incorporating automation to lower the overall operational burden on the RPM scanning mission. So one of the key elements that we found in performing this over the past 2 decades is that one of the things that are really important to have is, you know, a test bed and a controlled environment like this one that basically introduces all of the operational elements and allows us to test the systems and characterize them before we put them out in the field, because once they get out in the field, they have to function properly. Otherwise, they're going to impact commerce, right? And so this has been a critical element for success for us moving forward. And so today we're actually walking through one of the most important test beds that we have, the RPM test track. And you can see as we look around that we have lots of different configurations of RPMs installed. We actually have a configuration for every RPM that we have installed across the country. We have like this system here, which is what we have for what we call personally owned vehicles or cars or trucks. And then we have these taller systems that are a 4-panel system that's designed to scan buses, semi-trucks with trailers, as well as semi-trucks that are pulling sea containers, right? And then in addition, we're going to walk over here a little bit further. In addition to the RPM systems, we also have other supporting equipment that goes along with it. It's not just the detection system. So we have things like traffic lights, gate arms. We have camera systems. We have intercoms, and we even have the Customs and Border Protection booths where the control equipment associated with the RPM system is installed. Again, to try and make it as real world as possible so that we can put these systems through the paces before we put them out into the field and make sure that they're fully functional. So in addition to the deployed systems, we also have some next generation systems that we're testing, that we're trying to help DHS prepare to be deployed out in the field. And we've got one of those next generation systems that's sitting right over here with the gray panels on the inside. And then this actually system right behind us is also another next generation system. So we're working closely with Customs and Border Protection and Countering Weapons of Mass Destruction to prepare these systems, make sure that they're all adjusted properly so that, again, we put them out in the field, they're operationally ready to go. So in addition to the RPM systems, the test facility here also has a large variety of radioactive sources that we can put in front of the RPMs to test them. So sources like special nuclear materials like plutonium and uranium, the things that we're trying to detect, we can put them inside a cargo container and pull them through with a truck, simulate real world environments, test, evaluate, and make sure that the RPM systems are detecting what they need to detect. In addition to that, we also have common materials that are found within conveyances that come across a radiation portal monitor. You can see some of these blue and gray containers that are over here on the end of the track. Those are some of those common materials, and some of those materials actually have naturally occurring radioactive materials in them that produce a radioactive signature. Things like bananas, granite, and porcelain. And so one of the major challenges that we ran into in trying to deploy these systems was trying to figure out how to be able to detect the difference between materials that have a naturally occurring radioactive signature but aren't a threat to the nation versus the special nuclear materials, the things that we want to discuss. And so PNNL scientists and engineers work really closely with the RPM vendors as well as the operators to fine tune the system so that we could reduce the number of what we call nuisance alarms, or alarms that are realistic based off of these materials that have radioactive signature but aren't of materials of concern that we're looking for. And this is really important because any alarm that happens associated with an RPM must be adjudicated by Customs and Border Protection officers. And that's a pretty labor intensive process. And so the more nuisance alarms you have to deal with, the more operational burden to the officers, the less commerce that can actually get through and into the country. And so we spent a lot of time trying to optimize that. Another challenge that we face, that the RPMP team faced in deploying these systems across the country, is the wide variety of operational environmental conditions that we had to deal with. So on the northern border, for example, there are spans of months where the temperature doesn't typically get much above 0 degrees Fahrenheit. And then conversely, on the southern border, there are locations where the temperature is consistently above 100 degrees Fahrenheit for a significant amount in time. And so we've got to make sure that these systems, once we deploy them, can work in those extreme environmental conditions. And the way that we do that is by using large environmental chambers. And if we walk over here, we can actually see one. We've got one that's sitting right over directly across from this walkway. It looks like a cargo container on the back, but it actually has very sophisticated environmental controls inside of it. So we can place RPM components inside of it and put them through the paces in terms of cycling through temperatures, both at the extreme low and extreme high, to make sure that these systems will work properly. So, I mean, as you can see, the RPM mission is a really challenging problem that requires a strong multidisciplinary team, including radiation detection physicists, electronics engineers, software developers, construction design experts, system engineers and testers, and many more. And a national lab like PNNL is really well suited to take on some of these challenges. And working together with our DHS counterparts, we've been able to deploy the system, that's sustainable, and does the job that it's meant to do, protect the nation from, the threats that illicit nuclear and radiological materials pose. So I really appreciate everyone taking the time to join me on this tour. And at this point, I will take any questions if we have any.
Great, thank you, Kevin. We do have some questions coming through, so I'll go ahead and get started. Who determines where these systems can be deployed?
So that's determined by customs and, by DHS, by Department of Homeland Security, and particularly with Countering of Weapons of Mass Destruction Office and Customs and Border Protection. Together, they look at the need, the associated volume of conveyances that are going through at a border crossing or a seaport, and then they make a judgment call whether or not they want to do scanning with fixed RPM systems or use mobile systems or just do hand scanning if the volume is low enough.
Okay, and do you receive any exposure when you pass through a radiation portal monitor, like a dental x-ray?
So these systems are passive radiation scanners. They don't emit any kind of signal at all, so there is no exposure to anyone coming through.
Okay. And how many staff members at PNNL work on the radiation portal monitor project?
So, staff members at PNNL typically don't work full-time on a project. So I have approximately 300 staff, just over 300 staff members who participate in some fashion in terms of contributing their knowledge and efforts into the project. But if you look at it in terms of full-time equivalents, depending on how busy we are supporting deployments out in the field, I have anywhere from 40 to 70 full-time people working on the project at any given time.
Okay, and does the RPM system provide any localization of the source or just that a source was detected?
So there is some efforts to incorporate some newer algorithms based on machine learning that do some localization to give the operator who needs to adjudicate the alarm an indication, roughly of where the source was detected in the conveyance. But it's pretty rough at this point.
And are you involved in imaging of vehicle contents or just detection of radiation?
So the radiation portal monitoring project is focused specifically on just radiation detection with these passive radiation detectors. But, they are part of a bigger system that is, that does include imaging systems to look for things like illicit narcotics and other drugs, as well as stowaways. And so it's part of a bigger scanning system.
And what is the future of this technology? What's next?
So, basically what's happening right now is, the systems are working just like they're supposed to. Obviously, we haven't had a radiological or nuclear attack on the U.S. since these things have been started. So that's great. But we're looking to incorporate new technologies. It's been 2 decades since these systems were initially deployed. And so we're looking at putting out more sophisticated systems that are more easily upgradable, and also incorporate maybe, more sophisticated sensing technologies so that you can have a more integrated system. Because that's kind of the problem we're into right now, is there's lots of different sensor technologies that we can bring to bear on this, but none of them are really designed to be integrated. So getting that holistic picture that a CBP officer needs on a border, which is basically, do I stop this vehicle and search it, or do more, or do I let it pass? It's hard to do because they've got to look across all these different, sensing system results and make a judgment call. And so we're really trying to help focus more on the integration of the data across all these different platforms to help to make the job easier for a CBP.
And on the imaging systems question, is PNNL involved in any of those imaging systems that we're doing, where we had talked about if you can image the interior of what's passing through? Oh, and we may have lost our connection with Kevin. Ryan?
Sure, I can answer that. Yes. So while we are not specifically developing the technology associated with those imaging systems, we are working directly with Customs and Border Protection with those vendors to ensure that they're meeting specific specifications for the border and working in that environment. In addition, those particular systems, those large X-ray imaging systems, also could potentially interfere with the operations of the radiation portal monitors. And so we work with CBP and the vendors to ensure that they're placed properly at the ports of entry, ensuring that there's enough space between those imaging systems and the RPMs to ensure that they're not interfering with them.
Thank you. And we have a couple of other questions, and it looks like we lost Kevin for a little bit. Are you interested in answering those questions for us, Ryan?
Happy to do so, Megan.
Great, thank you. Are there any efforts to help automate the process officers take on with the RPMs?
That's a great question, Megan. In fact, we are heavily involved with efforts to ensure that as more and more ports of entry, in particular seaports, are beginning to move to automation, we're trying to figure out ways to make sure that the scanning process could also potentially be automated. And so we worked directly actually with the Port of LA Long Beach, the largest port in the United States, to ensure that those systems, the RPMs in particular, could be automated. So now you have a central facility that is in essence off-site that is looking at those images and the detection systems to ensure that if there are any alarms, they can send officers out in the field to deal with those immediately. But really, that is the future that we're seeing, in particular at some of these very large ports, like you see at Port of LA Long Beach, to move to automation. And so that's allowing us to use some of our expertise in data analytics, image analysis, and artificial intelligence and machine learning.
Great, thank you, Ryan. And it looks like we have Kevin back. Kevin, are you with us?
I am. Sorry about that. We had a technology problem here, but I think we got it resolved.
Understood. So Ryan answered a couple of questions for you. We do have a couple more. Does this technology predate 9/11? And what was the reason for developing the system?
I think my understanding, and this kind of predates my time on the project, but that there was some investigation going on into this technology and using it specifically for this application. And with 9/11, the desire to get these systems out there and working and protecting us was accelerated. So I think the technology definitely existed before. It has been used. Portal monitors have been used for other applications, for things like scrap yards, where they're looking to separate different types of metals and things like that, or looking maybe for radioactive material. But yeah, the technology existed before, but 9/11 really accelerated the deployment of it for this mission.
Ryan, did you have something to add as well?
Yes, no, I can confirm, as Kevin did, that it did predate 9/11. I think what you saw, as Kevin mentioned, is that there was certainly a large uptick in making sure that these systems were deployed. And in fact, the Department of Homeland Security, which was stood up in 2003, there was a presidential directive in 2005 that actually stood up a specific office focused on this mission set, what was then known as the Domestic Nuclear Detection Office. I had the pleasure and privilege of working at that office from 2005 through 2009. It now is known as the Combating Weapons of Mass Destruction Office. But many of those systems that were deployed, again, enhancements and refinements have been made in a number of ways. And in particular, the ways that PNNL has utilized our expertise in radiation detection to apply some of those enhancements to those systems have certainly helped to improve that process. And really over the years, we've helped to ensure that those Customs and Border Protection officers that are on the ground dealing with those alarms, that is not the only mission that they're dealing with. They have multiple other mission sets that they're working on. And so we've been able to help decrease those alarms such that they can continue to work on some of those other important mission sets that they encounter at the borders.
Yeah, I'm guessing, Ryan, you might have already covered what we're doing down at LA Long Beach, but initially, yeah, just to reinforce, initially, officers were basically assigned to each gate where these things were installed because they had so many nuisance alarms that they had to deal with. Now we can take a huge port like LA Long Beach where, there's, multiple ports of entry, as well as, 70 or 80 RPMs, and those can be operated by, just a few officers in a central command center.
Great, thank you. And what is actually being detected? Neutrons, X-rays?
So these systems actually have two different detectors inside of them. They detect gamma rays and neutrons. And we use both to predict the signature associated with the materials that we're interested in.
Okay, and I think we have just one more question. Are there RPMs in ports, excuse me, in ports or on maritime platforms?
Yeah, so all major seaports have RPMs, and basically once the large ships are unloaded with their containers and they're loaded onto trucks, before the trucks are allowed to leave the port, they have to go through an RPM. So all containerized cargo is scanned by RPM systems.
Okay, well, thank
And-
you. Go ahead,
And
Brian.
Megan, if I could also add, and in
Yes,
fact, something that was quite localized to our area, to the state of Washington, the Port of Tacoma actually had an environment such that most of their containerized traffic, as they were being offloaded from ships, would actually go directly onto rail. And so PNNL worked directly with the port as well as other national laboratories to come up with a solution whereby those cargo containers could be scanned before they were placed on that rail, such that you could continue to speed up the process and ensure that commerce was not directly impacted by that. So that was a nice example of something that we were able to work on in our own backyard. And that solution has now been deployed to multiple locations across the country.
Yep,
Okay.
thanks, Ryan.
And that being said, we actually did have one other question come through. Are other countries installing similar technology?
So actually, if we take a stroll over here, and hopefully the technology will stick with us. This first lane that we didn't take a look at, you'll notice some white portals that are installed in this first lane. These systems are actually deployed internationally by a component within Department of Energy, part of the Nuclear Smuggling Detection and Deterrence Program. And so we actually, help facilitate the installation of RPM systems abroad as well, through not through DHS, but through Department of Energy.
Okay, great. Thank you. Thank you again to everybody, Ryan, Dave, and Kevin, for the great tour and information on how we are providing the Department of Homeland Security with world-class solutions in airport security scanning and radiation detection at U.S. ports of entry. And thank you to all of you who took time out of your busy schedules to attend tonight's tour. I'd like to ask you for just a couple more minutes of your time to take a brief survey. At the end of the survey, you can also sign up to receive notifications about future tours, seminars, and other community events. And we should be seeing a link to the survey in the chat window momentarily. We also have recordings of past events you might be interested in, which can be found at pnnl.gov/events. And our final virtual tour, let me just share my screen real quick, is SynBio capabilities at PNNL on Wednesday, September 15th at 5 o'clock. On this tour, we will visit 2 laboratories at PNNL and learn how we are leading advanced research on microbiome engineering to obtain energy from industrial wastes and improve bioenergy crop health to make this future a reality. And we'll place the Zoom link registration or Zoom registration link in the chat window as well. So with that, thank you so much to everyone who joined us tonight. We hope to see you next week for our final virtual tour of the series. Thank you and have a great evening.